So we'll recognize a compound inequality problem just by the fact that we begin with more than one inequality on the page, right? So in the example of 3b4, we have x less than or equal to 2. We also have x greater than or equal to 5. In the problem that follows it, it actually doesn't really look like we have two inequalities, but secretly we do. One of the things that you can do with an inequality that looks like this, so this is called a triple inequality, is we can actually break this apart. There are two inequality signs here. There's a less than or equal to, and there's a less than right here. So what you can do in these cases, when it's not obviously a compound inequality out of the chute, is to take each of those signs and consider it on its own. So you'd first start by writing negative 12 is less than or equal to 4x plus 4. I'll copy that down here. This is not the problem that we're going to do together. This is going to be one of the ones that you do on your own. So take the first inequality that you see with the less than or equal to sign there and write it. And then separately, now cover up the first part and just take the second inequality, 4x plus 4 is less than 16. And in any case where we have a triple inequality like this in the beginning, the word that we want to put in between these two is and. That's really what it means when I write this triple inequality. This means that 4x plus 4 is both less than 16, and it also has to be greater than or equal to negative 12. So you can split it apart into that compound inequality explicitly. That's really a safe way to go, so that you know how to connect the work you'll do on this problem to the works we're doing in the other problems. But let's back up a step and just look very simply at this problem, which asks you not to solve this compound inequality, because actually each of these inequalities is already solved for us. The x's are already by themselves. So here we're focusing just on what it means to combine two inequalities together using one of our logical connectors. And in this example, the logical connector is the word or. When you see one of these words in a compound inequality problem, it's a good idea to circle it, make a note of it, make sure that you see it there, because the word that shows up there is super important to how you strategically end up solving a problem like this. But then once we make peace with that, we have two inequalities staring at us in the face. One that I'll highlight in green on the left here, x is less than or equal to negative 2, and one that I'll highlight in purple, x is greater than or equal to 5. And so the first step might be, and I'm going to recommend you do this even if the question doesn't ask you to do this, a good first step is always just to graph. So graph each inequality. Even when the question doesn't ask you to, graph each inequality separately first. On the same number line, but just draw them separately. So let's start with the one in green. X is less than or equal to negative 2. How would I sketch on this number line a graph that conveys the meaning of the green inequality? Where would I start? Or how would I start? Start at negative 2.
Go to the right.
Okay, so I'm going to start at negative 2. What kind of symbol do I want to put here at negative 2 to indicate that we're starting at negative 2? Really only have two options. Do I want an open circle or do I want a closed circle?
Open.
Open, and so what does an open circle mean? What's the difference between those? How are we making that choice? Put this inequality into words one more time. X is
Greater than or equal to.
negative 2. So yes, except I would exchange greater than for less than. So yeah, the symbol, one of the ways of keeping that straight, by the way, is that this symbol is pointing to the left. Right? If you think of it like an arrow, it's an arrow pointing to the left. And so that also indicates that that's the direction we're going to shade on the number line. So points left means less, means shade toward the left. But that changes the second piece of what you said. The first piece of what you said was less than or equal to, right? Which is what that symbol indicates. That means that the number 2, negative 2 rather, the number negative 2 is actually a part of that green inequality itself, right? Negative 2 satisfies this green inequality. So how do we indicate that on a number line? We want to indicate that negative 2 is actually a part of that set. We want filled in circle. So the mnemonic we talked about on Monday is that filled in circles are generally accompanied by less than or equal to or greater than or equal to signs. And those in our interval notation that we talked about at the end of class on Monday translate into square brackets. So those three types of symbols occur together. Right? If my inequality has one of these, then my graph is going to have one of these, and my interval is going to have one of these. Right? So I'm going to put a closed circle here to indicate that negative 2 is actually a part of the solution. And then I'm going to shade which direction? Left, because we want the x's that are less than or equal to negative 2. So now I've depicted the first of my two inequalities on the number line. I have kind of a visual learning preference myself. I tend to find it easier to make sense of a concept if I can see a picture. And so I'm a huge proponent of graphing. It helps me to understand, and I find that even if you're not used to doing it, there's a lot of benefit in drawing this out to help arrange your thoughts in a question like this. So there's the green inequality. The purple one, x greater than or equal to 5, what's different? How should we change our approach here? Where should we start our graph? We'll just start at a 5, right? Open circle or closed circle? Closed circle because it's greater than or equal to, exactly. Again, closed circles, greater than or equal to signs, square brackets, these things go together. So we'll put a closed circle at 5 because that indicates that 5 actually is part of this inequality. Because it's true that 5 is greater than or equal to 5, right? Because in particular it's equal. And then we'll just shade in which direction?
To the right.
To the right. Now one of the nice things about this problem is that these two inequalities don't overlap one another on the number line, right? They don't have any place where they have numbers in common. And so I can kind of get away with sketching them both directly on top of the number line itself. But it's a better practice, actually, if you have the room, and usually you do, to try and move them a little bit so that you can give them space to be one on top of the other. So sometimes what I'll do is I'll draw one of them just a little bit above the number line, and I'll draw the other one just a little bit below the number line. Because then, and the reason I might do that, in some problems, these two different graphs might overlap one another. And there you have some sort of tricky stuff that we'll do that we'll look at in another example. But the other thing that it does is it reminds you that we're not done yet, okay, in a lot of problems. Now, in this problem that just asked you to graph the compound inequality, we're kind of done. Except that at this point, we're still viewing each of these inequalities as something separate from the other, right? When what we really want is we want a single graph at the end of our problem, right? It doesn't do to have two separate graphs. Every inequality problem, every compound inequality problem has a single answer that combines the information in both inequalities in a particular way. And so that's where this OR comes in. So now the question is, how do I take the information that comes from both of these inequalities and OR it together? So if I have two logical statements, and they're connected with the word OR, so let me just pick something out of thin air. I am the President of the United States, or it rained in Bridgewater today. So there are two logical propositions. Each of those propositions is either true or it's false, right? That's what makes it a logical proposition. So if I combine these two into one assertion, I am the President of the United States, or it rained in Bridgewater today. How do we make sense of that as a compound statement? Do we think that that's true, or do we think that that's false? What do you think? Thinking about them as separate pieces, one of them is true, namely, which one? The second one is true. Yeah, I'm not the president yet. You never know. But the other one is false. But then if we're dissembling in that way, right, if we're kind of taking them apart and saying, well, one of them's true, the other's false, we haven't confronted them as a single compound statement yet. Right? I want to know not whether each one of these is true or false, but is this whole statement, I'm president or it rained today, is that whole statement true or is that whole statement false? It has to be one or the other because it's a logical proposition. Can't say that it's half true.
False.
False? Why?
Because you're saying something false in the statement, which makes it all false.
Ooh, good question. Yeah, so, all right, I like that way of thinking. If one piece of this puzzle is false, it makes the whole statement false. I'm going to claim that's not true for this statement. And this is why the word that we use to connect these two statements together matters. Here I'm using the word or. What does or usually mean in common language, common English vernacular?
This happened, that didn't.
Yeah, no, it's possible for one of them to happen and the other one not, and still to be okay in some way, right? Saying or leaves open the option that one of them might be false, but as long as one of them is true, then we're good. I can confidently assert that it's true that I'm the president or it rained in Bridgewater today, because it rained in Bridgewater today, so that statement's true. So that's the thing about or, right? Or means that our final answer here is true as long as one of the subordinate clauses, one of the pieces, is true. So it doesn't matter how many of the pieces are false. As long as one of the pieces is true, then the or compound statement is true. So it's kind of weird. If we wanted something that's more like what Joe was saying, well, there are ways of combining together compound statements such that in order to be true, every piece needs to be true, right? So that one lie makes the whole thing false. We would just use a different connective. What would I replace the or with to convey that message? Do you think? Yeah, you can kind of look at the agenda for the day on the board and get that idea. Right, exactly. So that's the difference. For an or, it's true as long as one of the pieces is true. But for an and, so this statement is true. But for an and, I would be saying, hey, I'm the president and it rained in Bridgewater today. And in that case, we do need every one of the pieces to be true in order to make the compound statement true. So this is kind of a logical digression, right? This doesn't really have to do with math, but it will in a second. So for an and is only true if all pieces are true. Right. So, what does this have to do with inequalities and how to combine inequalities together? Here's how I like to think of it. So, looking at the particular example that we're working on right now, I want to come up with a single set that consists of all the points, all the x's, for which x is less than or equal to 2 or x is greater than or equal to 5. So in order to belong to that final answer that we need, right, we know we only have a single answer to this problem. In order to belong to this final answer, we need to either belong to this set or to belong to that set. Right? And so what an or does is it just combines the two intervals together and takes all the points that belong to either. So or consists of all points satisfying either. Inequality. Whereas for an and is only true if all of the pieces are true. And so in that case, an x would belong to the solution, an x would belong to the compound inequality, only if it met both of the criteria in the compound inequality simultaneously. So that would be a very different It's a very different way of combining our two answers. So and consists only of the points which meet all criteria. Since our compound inequalities are generally only going to consist of two separate inequalities, you might think of the word both here instead of all. But in general, if we had more, we would have to require that they met all criteria. And then, just for the sake of shorthand, in an and statement, we tend to look for the overlaps only. Right? We're going to look for the places where those two intervals overlap one another, whereas in an or, we just combine everything. Combine everything from both. From each, I'll say. So in our example, if I were to OR these two inequalities together, if I take a point which belongs to the green set, does it belong to our final answer? It does, right? Because, remember, an OR doesn't care. An OR says, as long as you belong to one or the other of these sets, then you're in, right? So everything that belongs to the green set will definitely belong to our final answer. And what about everything in the red set, or the purple set? Same deal. Everything that belongs to the purple set also belongs to my answer. So, all in all, we've now combined our two inequalities into a single inequality. And that's that. So I've tried to use colors here strategically to indicate the difference between what we had before. What we had before were the purple and green, right? These two inequalities as their own separate entities. But then there's the step that everyone forgets. Not everyone, but a lot of people forget. And is that my answer needs to be a single answer. And so my answer needs to be the red set that combines both. Last thing is to bring back interval notation that we talked about some on Monday. And now it's time to come back to the table about it. So let me make some space. And let's talk about how we might express this red set, which is our final answer to this problem. How do we express that red set using interval notation that we talked about last time? Well, remember, every interval consists of four things when we express it in notation. 1, 2, 3, 4. And then there's a comma in the middle. But we have four decisions to make every time we go to write an interval. We need to decide what the endpoints of that interval are, the lower endpoint and the upper endpoint. And then we also need to decide on what type of braces to put here and here, right? By which I mean, do we want closed brackets or do we want open brackets? So we have four things to decide. But what's the problem with our answer here? There's not a clear left endpoint and there's not a clear right endpoint. Because this piece of our answer extends all the way back to negative infinity. This piece of our answer extends all the way right to positive infinity. But it's not enough to just say minus infinity is the left endpoint, plus infinity is the right endpoint, because then we would miss out on all the action happening here in the middle where there's actually a gap. So this is a little different example than the ones that we've seen before. The good news is we can take it one piece at a time. So let's start with what used to be our green set. X is less than or equal to negative 2. Remember, that's this solid circle shaded to the left. How would I write an interval that captures just that piece of the set? What would that look like? What would the endpoints be, first of all? What's the left-hand endpoint for the green set? How far to the left does this green set go? Green set extends infinitely far to the left on the number line. So we'll use negative infinity as the left-hand endpoint for that set. how far to the right does this end up going? Well, this one's easy. You can read it off the number line, -2. Right? The uppermost endpoint for this is -2. So now we figured out our endpoints. Now we just have to make the decision about what kinds of braces to use. Let's start with -2, the right endpoint. Do I want to use a square bracket or a round bracket? Remember, the square brackets indicate inclusion of that number. Round brackets indicate not inclusion, exclusion. So which of those two do I want for -2? Because -2 is included in the set, we use a square bracket to indicate that. How about -infinity? Is -infinity actually a part of the set? Is it a number that I can plug into this inequality and get a true statement? It's not a number at all. And so the statement, is it a number that we can plug into this statement to make it true, is false. That was me trying to be too brutal. So anytime you see an infinity or a -infinity, it always gets a round brace. That's not something to ever overthink, right? Anytime you see an infinity, because it's not a number, we can never include it in any of our sets that answer an inequality. So the green set we can write using that interval notation. The purple set that we had before, we also can use interval notation to express it as a separate piece. And for that, we make the same decisions. The endpoints are 5 and positive infinity. Positive infinity never included. 5 is included in this, again, based on the greater than or equal to and based on the solid circle on the graph. But at this point, I'm again using colors here to indicate we have two separate answers. So we need to combine these together to make one single answer that we can plug into Alex or to write into our exam blank, or whatever, right? And so this is the piece that we haven't talked about yet. To combine two disjoint sets. These sets are disjoint, meaning that they don't overlap one another. They're two separate, totally separate parts of the number line. To combine them together into a single set, we're just going to use this weird-looking U, uppercase U. Well, I wouldn't even, I hesitate to call it a U because don't write it like this. I won't laugh at you for it, but other math professors just, they have these sensibilities about their symbols. So a U without the extra little line on it. This little U is the union symbol. And the union symbol for sets, intervals, is just the notation that connotes the or, that the elements in our final answer consist of these values as well as these values. Anything that belongs to one or the other of these sets will be a part of this ultimate set that is our final answer. So our final answer then looks like this. Minus infinity to -2 with a square bracket. U, 5 comma infinity, with a round bracket that way.